Welcome to Empowered Learning. This is the final video in the video series on infinite series and their uses in calculus. The introduction, that is. And so this final video, we're going to continue on with the examples that we were doing in the part 2 video, but we're going to switch gears here a bit and show an application of how a geometric series in particular can be used to express a repeating decimal number as a fraction. So with this first example, we see that this number 6.254, where the 54 is repeating, we want to write it out in such a way to where we can actually see some type of pattern going. And of course, this 6.2 part, we just go ahead and write that out. And since this is a repeating, we know this is going to be 0. If we just write out the rest of this, all this is going to be 0, 5, 4, 5, 4, 5, 4, continuously, 5, 4, 5. I keep on writing the 0 there. So 5, 4 continuously. Okay. And it just keeps on going. So the thing here is that the first term that we're doing is just writing the 0 plus the 5, 4. And then the second term, so this is the first term here for the pattern. And then for the second term, we notice that we have 1, 2, 3 zeros and then 5, 4 for the second term. And then for the third term here would be 1, 2, 3, 4, 5 zeros, and then 5, 4. So that's what you see here. And of course, we can just continue on with that. Now, if we read our decimal numbers in proper form here, we see that the 0.054, we actually pronounce that as 54 1/1000ths. And so here that lets us know exactly what to write that like as a fraction. Of course, here we have the tenths, hundredths, thousandths, 10,000ths, 100,000ths. So this will be 54 100,000ths. And of course, that is what this fraction looks like. And of course, if we go ahead and write this last one, this is 54 10,000,000ths. And this is what this fraction looks like. So now at this point, we need to find a way to be able to express this in such a way to where it's a little bit more compact. The one thing that we see that's in common with these last three terms, before we have the ... is that all of them have a common factor of 54. And we also know that 1 divided by 1,000 is the same as 10 raised to the negative 3. We know that 1 divided by 100,000 is going to be 10 raised to the negative 5. Okay? And of course, we know that both of these, because 1,000 could be expressed as 10 raised to the 3, and thus the reciprocal of 10 raised to the 3 is just 10 raised to the negative 3. And same deal here. We know that this is going to be 1 divided by 10 raised to the 5. So the reciprocal of that is 10 raised to the negative 5. So we see all that, and we factor out the 54 that is out of each of these terms, which is here. And we see this pattern. And of course, if we write that as a fraction, it'll be 1/10 raised to the 3 for the first term, 1/10 raised to the 5 for the second term, 1/10 raised to the 7th for the third term, so on and so forth. And so it's this part that actually acts like a geometric series. And so here we know that this 6/2 part is just 6 2/10, which is 6 1/5. And of course, we could rewrite that as an improper fraction. And so we have just 31/5 plus 54 times whatever the sum of this particular series ends up being. And so here we see that this portion here is fitting the profile of a geometric series where a is 1/10 raised to the 3, or 1 over 1,000, and our r is going to be 1/10 raised to the 2, or 1 over 100. So we go ahead and substitute all that in here, and we know that this result is just going to be a divided by 1 minus r, where your a is basically 1 divided by 1,000, and your r is 1 divided by 100. And so we go ahead and plug that in here, and then it's just a matter of doing a computation to get to the final answer. And we see that when we do that, we end up getting 344 over 55. And so that would be the way that we would express this particular repeating decimal number here as a fraction. And so this is an example of why we consider repeating decimal numbers as rational numbers, because it can be expressed as a fraction. And of course, by definition, any number that is considered to be rational can be expressed as a fraction. Okay, so in our next example, we want to do the same thing, express this particular number here as a fraction. And so we see here that this is just 0.2 repeating. So this could be looked at as 0.2 plus 0.02 plus 0.002 plus 0.0002, and then continuing on. Okay. Now, if we read this correctly, this is going to be 2/10. This will be 2 100ths. Next term will be 2 1,000ths. Next term will be 2 10,000ths. And so on and so forth. So of course, if we want to look at this, this 2/10 here, we could look at this like 2 times. So we're going to factor out the 2 and all of that. We'll have 1/10 plus 1 100th plus 1 1,000th plus 1 10,000th. Continuing on. Of course, we could express 1/10 as 1/10 raised to the 1. Of course, we know that 1 divided by 100 is the same as 1 over 10 raised to the 2. Thus, we could express just 1 over 100 as 1/10, all that raised to the 2. Of course, this next one could be expressed as 1/10 raised to the 3. Next one, 1/10 raised to the 4. So on and so forth. So here we recognize that we have 2 times some geometric series, and the first term of this series, so we're going to write it in summation form. The first term in this series is going to be 1/10. Okay. And we see that the common ratio is also 1/10. So we're going to say this is 1/10 raised to the n minus 1. And let's make that look a little different here. And of course, we know that this 1/10 here is A, and the other 1/10 is R. So this sum that we're going to have here is just going to be 2 times A divided by 1 minus R, where that A is going to be 1/10, that R is also going to be 1/10. And to make this look nice, we'll just multiply the numerator and denominator by 10. And this will just end up being 2 times 1 over 10 minus 1. And of course, that will just end up being 2/9 at the end of the day. And so that is how we could express the number 0.2 repeating as a fraction. So in our next example, we want to do the same thing. And what we notice here is that we have the 1/5, that's the part that repeats. So here we're going to say 5.2. And then we're going to do that plus 0.015, because these are the first two 1/5s that repeat, plus 0.000 to cover these 3 zeros here. And then we'll write the next 1/5 plus point. Now we have 1, 2, 3, 4, 5 places to cover. And then we got another 1/5. And of course, that will just carry on. Now we know that 5 over 2 is the same as 5 2/10. We also know here that if we read this particular decimal number, it's going to be 15 1/1000ths. Okay. And of course, if this is 1/1000ths, then this is going to be 100,000ths, because we have the tenths, hundredths, thousandths. The tenths, hundredths, thousandths, 10,000ths, 100,000ths. Yeah, I think I said that wrong. Yeah, so this is tenths, hundredths, thousandths. So it's thousandths, and then it's 10,000ths, hundreds, thousandths. Yeah. So this will be 15 over 100,000. Then of course here, if this place here is the 100,000ths, then this is the millionths, 10 millions. So this will be 15 over 10 million. So here we know that 5 2/10 is the same as 5 1/5. And here we have in common a 15 in all these terms. And what we got left is 1 over 1,000 plus 1 over 100,000 plus, and I forgot to do the plus dot 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 here. This is 15 over 10 million and dot dot dot. And as a improper fraction, 5 1/5 is the same as 26 over 5. And of course here we know that 1 divided by 1,000 is the same as 1 over 10 raised to the 3. For this next one, since we have 1, 2, 3, 4, 5 zeros, and this one has 1, 2, 3, and this is going to be 1 over 10 raised to the 5. And of course, 10 million has 7 zeros, so this one will be 10 raised to the 7 in the denominator. And we'll just keep going. So now once we're here, we know that this is going to be a geometric series where the first term is going to be 1 divided by 1,000, basically, a 1 divided by 10 raised to the 3. So I'm going to say this is sum of n equals 1, infinity, and that's going to be the first term. And we know that the difference in between, well, the ratio in between 1 over 10 raised to the 5 and 1 over 10 raised to the 3, or put another way here, 10 raised to the negative 3, 10 raised to the negative 5, the ratio for that is going to be 10 raised to the negative 2, or 1 over 100. So here we're going to rewrite this way. Write it like this. And then that's going to be the n minus 1 there. All right, so I'm going to clean up some of this formatting just a little bit here. All right, so we got that cleaned up here. Again, this is going to be our A, all of this. And this is going to be our R right here. So here this means that we have 26 over 5 plus 15 times A, which is 10 raised to the negative 3. I'm just going to write it in that form, over 1 minus R. This is 10 raised to the negative 2. So to get this in a format that's going to look nice, one of the things that we could do here is multiply the numerator and denominator by 10 raised to the 3. That'll clean this up and make it look a little bit nicer. So we have 26 over 5 plus 15 times, and now 10 raised to the 3 times 10 raised to the minus 3 is just 1. And then here we have 10 raised to the 3 times 1, which is just 10 raised to the 3, minus 10 raised to the 3 times 10 raised to the minus 2 will leave me a 10 raised to the positive 1. And so this is 26 over 5 plus 15, and this is basically 1,000 minus 10, which is going to be 990. And then from there, of course, this just ends up being 26 over 5 plus 15 over 990. All right, so close this out here. We'll just simplify what we got going on. And 990 is the same as 99 times 11. Yep, sorry, I meant 99 times 10. And we know that 99 is 11 times 9. So what I was trying to do in my head there earlier is kind of write it this way. So we're going to say 9 times 11 times 10. Okay. And from that, we know that 15 and 10 both have a common factor of 5. So 5 will go into 15 3 times, and 5 will go into 10 2 times. And we also know here that 3 and 9 have a common factor of 3. So here 3 will go into 3 one time, and 3 will go into 9 3 times. So essentially here we have 26 over 5 plus, and that looks like we have 1 over 66. So now we can just close this out by doing 26 times 66. So I'll just do this 26 times 66 plus 1 times 5, all that over 5 times 66. And if we do that, we get 1,716 plus 5, all that over 330. And final answer just ends up being 1,721 divided by 30. And that is our final answer for that. Of course, yeah, it takes a while, to do the computation part, but we see that once we have the geometric series there, knowing this is a whole lot shorter than actually just summing it out on your own. Okay, and that's really what I'm trying to showcase here. All right, so let's move on to our next examples. Okay, so for our next set of examples, we want to use the nth term test or theorem for divergence to show that the given series that we have is going to be divergent, or that the test is going to be inconclusive for us. And so before we start with this, I want to address what this part is about the test being inconclusive. So if you remember the nth term test for divergence, which was our basic fact 2, we knew that unless we had a situation where the limit as n approaches infinity of the sequence goes to 0, unless this happens, we know that our series, whatever it is that we're looking at, our series here will diverge. Okay? And so the point here is that if we take the limit of our sequence that makes up the series in the first place, and if it goes to 0, then there's a chance that it may converge or it may diverge. Okay, it's kind of open, and so that's what is meant by the test is inconclusive. So if we just come here and say, all right, well, this is the corresponding sequence, we take the limit of it, it goes to 0. Well, it could converge or it could diverge, but if this limit equals anything other than 0, we know definitely without a fact that that particular series will diverge, and that's the end of the story. Okay, so in this case, we're going to let this 1 divided by n plus 15, we're going to let that be a sub n, and we're going to take the limit as n approaches infinity of a sub n, which is essentially this here. And of course, if I plug in an infinity here, I'm going to have this case goes to infinity, which means that this is going to go to 0. So because of the fact that this goes to 0 here, this meets this condition. Thus, we see that the nth term test for divergence is inconclusive in this case, meaning that we can't tell whether that particular series is going to converge or diverge just by using this particular test. So we would have to do something else in order to do it. And as of right now, the tools that we have available to us won't allow us to do anything else. Now, of course, if we move forward here and we start talking about like the integral test, that is a subject that we talk about after this one. we looked at P series and we looked at comparison tests and all that good stuff, then we would have a way to be able to further analyze the situation. But with the current knowledge that we have right now, all we can say is that it's inconclusive whether this particular series is going to be convergent or divergent, just based upon the nth term test for divergence. Okay. All right, so let's look at our next example. So for our next example here, we want to write out the first few terms of this particular series and then figure out what is going to be that the series sum. So let's go ahead and do that. So of course, when n is 0 here for this particular series, we'll just plug in 0 here and here. And of course, anything raised to 0 is 1. So that means that we'll call this a sub n here. So this will be a sub 0 rather. And this would be 1. And I'm just going to come here and call this a sub n. So when n is equal to 1, then that's going to be a sub 1. And that's just going to be a negative 1 raised to the 1 divided by 6 raised to the 1, which is just going to be a negative 1/6 rather. And then n equals 2 give us third number in the sequence, a sub 2, which is going to be a negative 1 raised to the 2 divided by 6 raised to the 2, which is a positive 1 over 36. And n raised to the 3. Same thing here. 1 raised to the 3, 6 raised to the 3, and this is going to be a negative 1 over 216. And if I did a raised to the 4, or n equals 4, that would give me a raised to the 4. 6 raised to the 4 here, which would be a positive 1 divided by 1,296. So we listed the first 4 terms. What we can see is that the signage of each term is alternating, and that's fine, but we see as the numbers alternate in sign, the higher the value of n goes, the lower the number gets. Okay, so we kind of have a situation where we're starting off positive, negative, positive, but less so than the other one, negative, more so than the other one, and it just keeps on doing this. So that is what, if we actually graph this particular sequence, that's what it would look like. Now, we want to know what is the sum of the series. Well, if we look at this, this kind of has the look of a geometric series, but it's not quite in the form that we're used to seeing there. So we could take this, and since negative 1 and 6 are both raised to the n, we could rewrite this as a negative 1/6 raised to the n, like that. And so to get this in the form of the geometric series that we're used to seeing, where the counter in here starts at 1, we're going to have to actually list out what that first term is here. And of course, if you plug in a 0 here for n, negative 1/6 raised to the 0 is just going to be 1. So we just have 1 there, and then this will be a negative 1 over 6 here, raised to the n minus 1. And in writing it like that, of course, if n is 1, we plugged it in here for n. We have 1 minus 1, which is 0. Anything raised to the 0 is 1, and 1 times 1 is 1. So that kind of works out the same way. So what this tells us here is that our a is 1, our r, our common ratio, is negative 1/6. And so that means that the sum of this particular series is just going to be a divided by 1 minus r, which of course a is 1 again, and r is going to be a minus 1/6. So this would be 1 over 1 plus 1/6, which is the same as 1 over 7 over 6, which the reciprocal of 7 over 6 is 6 over 7. So this would be what the sum of that particular series would be. Okay, so let's move on to our next example. So for our next example here, we want to find a formula for the nth partial sum of this particular series that we're given and use it to determine if the series is going to converge or diverge or not. If the series actually does converge, we want to find its sum. So before we get started here, we want to kind of get an overall view of what it is that we're going to be doing and why. Okay? So if we look at this particular series here, we notice that it is not a geometric series. We notice that we can't consider it to be a harmonic series because of the fact that it has multiple terms, and just because this particular term is harmonic doesn't mean that the entire series is harmonic. And thus, here in the second term, we know it looks closely to, it looks like it's related to a harmonic, but it is not, because it's not exactly something divided by n, where that something is just a constant number. Okay? So we can't use the assumptions of the geometric series, can't use the assumptions of the harmonic series. So of course here, since we have the difference in two terms here, we can actually telescope this thing to see what our sequence of nth partial sums would be. And then we want to take the limit of that. So why do we want to take the limit of the sequence of partial sums? Because we know, we learned earlier that if the limit of the sequence of partial sums equals to a real number, meaning that it exists, then what that tells us is that our corresponding series that this sequence of partial sums came from, which is what this is going to be, and we'll call it a sub n. So this particular series here is guaranteed to converge. Okay. So if we can find a way to express the sequence of partial sums as an algebraic function of n, and we take the limit of that, and it actually equals to a real number, then of course we know automatically without anything else that this particular series here will converge. And whatever this limit actually ends up equaling is what that particular series will converge to. Okay, so that is the idea here. And so that's why the first thing that we're going to do is try to figure out what our sequence of partial sums of this series will be. So we start off here. And matter of fact, I'm going to move this down here. Just going to do it like this. So we're going to say, come here, and then we're just going to start listing. So when n is 1, we will have 3 divided by 1 over 3 divided by 1 plus 1, which is 2, plus when n is 2, we'll have 3 divided by 2 minus 3 divided by 2 plus 1, which is 3, plus we'll have 3 divided by 3 minus 3 divided by 4, plus 3 divided by 4, and this is minus 3 divided by 5, and so on and so forth. Okay. So here, if we look at this, we see that when n is equal to 1, we just have this these first two terms here. When n is equal to 2, we see that these two terms reduce to 1. We see when n is equal to 3, these two terms reduce to 1. And we see here when n is equal to 4, this term and this term, sorry, I've been saying reduce to 1, they cancel to 0, sorry. So at this point, what we see here is that we have this term and we have this term for a given value of n. And so what this ends up being at the end of the day, let me erase this. So therefore, S of n for this is going to be 3. And for here, notice that when n is 4, my denominator here is 1 more than that. And notice here that my numerator is 1 less than that. Okay. But we saw that we had 3's in all of these. So here I would have to keep this as a 3 on top, but this will be n plus 1 on bottom. Because of course we saw that that was actually changing. But 5 is 1 more than 4. And so since n is going to be 4 in this case, 5 is 4 plus 1, which we can re-express that as n plus 1. So this is the sequence of partial sums for the series if we were to try to get n terms of it. So now from here, if we do the limit as n approaches infinity of S of n, that's just going to be 3 minus 3 over n plus 1. And of course we got infinity plus 1 there. All that goes to 0. Result is 3, and that is a real number. And since the limit of the sequence of partial sums equals a real number, what that means is that this particular series here, which is this one, will end up converging. Okay. So here we know that therefore this particular series will converge to 3. And we know that because, of course, the sum of this for n terms is just going to be S of n. And as n approaches infinity, that is going to 3. Okay. So that's how we know that. All right, let's move on to our next example. Okay, so for our next example, I've already written this out, but it's kind of the same flavor here. We have a series that is made up of two separate sequences that we are subtracting one from the other. So we know that, of course, it's not a geometric series. We know that it's not a harmonic series either. So what we're going to try to do is telescope it out. And here, all we're doing is just listing terms here. So we have natural log of square root of 2 minus natural log of 1 for when n is equal to 1. And of course, if n is equal to 2, plug in a 2 here, plug in a 2 there, we get the natural log of square root of 3 minus natural log of 2. Of course, when n is 3, plug plug in here, we get natural log of square root of 4 minus natural log of square root of 3, so on and so forth. And what you see here is that this natural log of 2, natural log of 2 cancel to 0. This natural log of 3 and that natural log of 3 cancels to 0. You see here we got natural log of 4, natural log of 4, natural log of 5, natural log of 5, natural log of 6, natural log of 6. Okay, and so if we stopped here right at n equals 6, what we would see here is that the terms that we have left, if we kind of look here, of course, this is 0, so this is automatically going away. So everything is pretty much going away here, except for whatever this particular term is here. And so we notice that if n is 6 here, 7 is 1 more than 6. So we would have natural log of square root of n plus 1. That would look like what the nth partial sum of this particular, well, the nth partial sum of this particular series. Yeah. So because of that, we see that this is going to be what we need to take the limit of. And of course, if the limit of this ends up equaling a real number, then we know that the corresponding series will converge. Otherwise, it will diverge. So of course here, went and wrote this out. Just took the square root as n plus 1 raised to the 1/2, in fact, and put it out here on the outside of the logarithm. Just dealt with this, and of course we know that that's going to go to infinity. So that tells us that this particular limit is not going to exist, which means that the series that we were looking at will definitely diverge. Okay. All right, so let's look at our last few examples. So for this example, we want to find the values of x for which the given geometric series converges. We want to also find the sum of the series as a function of x for those values. So this problem here is telling us that we have a geometric series, but we're trying to figure out the values of x that will force it to be a geometric series that converges. And so the motivation for this example is that when we get to the point, if you keep watching these videos, when we get to the point to where we actually want to express those functions that I mentioned in the part 1 video, where we're going to try to take the antiderivative of them, and they're not going to have an elementary function antiderivative to go to, we're going to have to express it as a polynomial approximation. And so one of the things that we do in trying to get those polynomial approximations for those functions that don't have a elementary function antiderivative for it is we want to figure out, hey, we know that this polynomial will work, but for what range of x values will this particular polynomial lay very close to or closely mimic the actual function, whatever it is. Okay, and so that's kind of the motivation behind this particular example here. So what I'm going to do to start this problem off is we'll go ahead and do summation as n approaches 0 here of, the summation n equals 0 to infinity. And we're going to write this together as 7x all that raised to the n. And of course, if we were to plug in 0 here for n, here and here, we would get 1 as our first term. So we're going to rewrite this in the normal way that we're used to looking at geometric series, where our counter n is equal to 1. And our first term there would be a 1. And so this would be 7x raised to the n minus 1. That was the case. And so from here, we know that this particular geometric series, so here we'll say this will converge if 7x is going to be in between -1 and 1, which basically means here that x has to be in between a -1/7 and a +1/7. And of course, in interval notation, we can write it this way. So this is the interval of x values for where this particular series will converge. And they also asked us to find the sum. So here we know this. We know that that sum is just going to be a divided by 1 minus r. Where here we know that 1 is our a and 7x is our r. So 1 is our a, 7x is our r. So this would be the sum of that particular series if we were to add up all the terms, all the infinite number of terms. All right, so let's look at our last example. So for our last example, we want to do the same thing as we did for the previous one, which we want to find the values of x for which this particular series, if we force it to be geometric, will converge, and then find out in terms of x what the series will actually converge to. So we see here that we have an alternating portion of this particular sequence here that's making up this series. I'll try to erase this. Not working for me. Okay, so I'll pause the video and erase that, and then we'll continue. So we see that this alternating portion of the partial sum sequence function, which is of course this -1 raised to the n, it's not going to affect how the series converges as long as our a and our r are such that, of course, a is a real number and r is a number in between -1 and 1. Okay, so all that's really going to happen is because we have this alternating portion to it, if it starts off high, it'll go high, low, like this. And if it starts off low, it'll go low, high, and then it'll do like this. So no matter how it works, it's still going to be the same. So here, what we can do is we can go ahead, since we have powers of n here, we can go ahead and just say x minus 4, all that times a -1, which is here. And then, of course, we do the negative of these terms, and we'll end up with just 4 minus x, all that raised to the n. And here I've kind of listed it out to show you what this would look like. So we would have 4 minus x raised to 0, 4 minus x raised to 1, 4 minus x raised to 2. And I really did this just to basically show you that this first term is going to be 0. Sorry, this first term here is going to be 1 here. And so because of that, that'll be our first term. So this would be like a 1 right here times 4 minus x raised to the n minus 1. And of course our a would be 1. And that's tied to what that is there. And our r, or our common ratio, would be this 4 minus x. And of course, 4 minus x would have to be in between negative 1 and 1, which means that negative x is going to be in between a negative 5 and negative 3. And of course, if I multiply all sides of the inequality by negative 1, we essentially see here that x is in between 3 and 5. And so we know from that this will be a geometric series as long as x is in between these numbers. And for here, we know that this corresponding series, it is going to converge upon this number, where again we know a is 1 and r is going to be 4 minus x. So a is 1, r is 4 minus x. Distribute the negative here, and we see that once we do all the work, we just end up with 1 divided by x minus 3. And so, of course, we would have to know for what values of x will that work. In this case, everything that is strictly in between 3 and 5. Okay, not including 3, not including 5. As long as you have that, then we know that whatever this series was that we were dealing with here in the beginning, we know that as long as these x values are in between 3 and 5, we know that we're going to have a series here that will definitely converge. Okay? All right, so with that being said, this concludes the part 3 video for our discussion upon infinite series and how we use them in calculus. Of course, this is the intro. So if you're following my videos, in the next video that I will do will be one on talking about p-series. And so we'll also be talking about the integral test in general. And of course, the p-series is going to be related to that. And we'll find some other ways to be able to figure out if a particular series is going to converge or not by now using not only just what we know about certain series such as geometric ones and harmonic ones, but we're also going to kind of throw back into calculus and start doing integrals and see how all that works to help us out as well. All right, so I hope this video helped. I hope this series helped, and I hope to also see you in the next video series. Take care.